All right. Professor Tim Wong, it's my distinct pleasure to introduce fellow chemist Tim Wong, who joined us recently from Virginia Tech, where he spent over 20 years on the faculty, serving as Associate Dean and Director of the Macromolecular Innovation Institute. Tim has numerous awards to his credit, including the 2015 Virginia Scientist of the Year Award, the 2010 Virginia Tech Alumni Research Award, the American Chemical Society Polymer Science Collaborative Research Award, the Dahlquist Award from the Adhesion Society, the 2019 American Chemical Society Rubber Division Thermoplastic Elastomer Award, and the American Chemical Society Polymer Division Mark Scholar Award. Dr. Long has obtained over 60 patents for his research discovery. He's a member of advisory boards for leading journals and was recently appointed as editor-in-chief of Polymer International. With that, I'd like to introduce Tim to tell you about drowning in plastic. What are the alternatives to keeping people and the planet safe? Tim.
Hi, thank you very much, Steve. Let me see if I can share my screen while everyone is sipping their cocktail. If I can do that. And if you guys can give me a indication that it's all there, I'll be happy about that. All right. Well, let's see, I put that in slide mode. Okay, well, thank you, Steve. That was a wonderful introduction. Too many awards mentioned, but I really should give a big shout out to my students, right? The students are really what make things happen, right? Professors, we come up with crazy ideas, but the students take those ideas and make them reality. So a big shout out to them. I also noticed a lot of students tonight. They're not in the laboratory right now, which is okay. I see a lot of postdocs, faculty, friends, and people I haven't met yet, but hopefully I get to meet in the future. So welcome. I did make my cocktail and I'll go ahead and toast you. How about that? Okay, so as Steve mentioned, my name is Tim Long. I've been at ASU for all of about, I'd say about 9 months. So I don't recommend moving cross country during a pandemic. It can be a somewhat interesting experience, to say the least. But it's great to be here. And what drove me to ASU? In a single word, that driving was sustainability. I honestly have not seen another institution in this country, perhaps the world, right, who has a sustainability mission as strong, as encompassing, as intersecting, as convergent, right, as the sustainability mission here at ASU. So it's great to be here. And really the center I lead, the Center for Sustainable Macromolecular Materials and Manufacturing, the name says it all, right? We are interested in sustainability, right? And we'll define that together. We'll debate that together. What does that mean, right? How does it differ from green chemistry? And then we'll have macromolecules, plastics, polymers, gels, networks, thermosets, thermoplastics. Depending on the table that you sit at for dinner, you're going to use a different term. And then we're looking at materials quickly becoming a top 5 program in the nation devoted towards macromolecular science and engineering. But the other word that we crafted together, I met with Steve and Josh, was the word manufacturing. Right? Putting that in the name of the title says a couple of things. It says, hey, we can discover things in the laboratory, but at the end of the day, it's getting them into the marketplace, right? Into people's homes, changing communities. Right, that's really what we're all about. It's this whole idea of molecules to manufacturing to marketplace, right? That's the vision, that's the continuum that we're looking at. So I thought I'd start with a couple of chemistry jokes. If you've ever had a chemistry class, especially organic chemistry, every chemistry professor has to show a joke. So I thought I'd start out at least by giving you a plate of spaghetti or pasta. Right, this is a normal model that scientists use to kind of represent, right, macromolecular structure, very long chains, very entangled. Yeah, there might even be a meatball thrown in, right? This is a model that we often use, this idea of spaghetti. So it allows me to use my favorite joke with you. And one of them is, what do you call a fake noodle? An impasta. Now that is a joke you can use at home. I think that will resonate with just about everybody you can come across. We also have to learn terminology. I'm going to give you some terms this evening, a few, just to get us so we can communicate. But no, a catalyst is not a record of the cows you own. Now, this one I sometimes have to explain. Cattle list, right? So anyways, right? Hopefully you got a chuckle out of that. Maybe the cucumber twist helped in a little bit of a way. But anyways, that's another joke I love to show. A photon checks at the hotel and asks if any help is needed with their luggage. The photon replies, "No thanks, I'm traveling light." Now that's a good one. You know, even the physicists are going to laugh at that one, right? I think that's a good one, right? I'd make another chemistry joke, but all the good ones are gone. Okay, hopefully you got that one. All right, let's get started. Hopefully I gave you time to enjoy your cocktail. And again, I wish, like Steve said, I wish we were in that modern restaurant together, and hopefully that day comes soon. But until then, let's talk about science. Let me give you a sip. Maybe let me give you a gulp of science, right? I'm going to turn on the fire hose a little bit, get us thinking, challenge you, maybe irritate you. I don't know, but getting us thinking about the world that we live in, the consumption that we're using, right? And how we can cope and prevent, right, drowning in plastics. So let me start out with this particular data. Again, I'm only going to take about maybe 10 minutes of time to get the conversation rolling, right? And then once it's rolling, let's have a really lively conversation. But let's look at this data, right? It's pretty amazing. It's kind of scary. What's the primary plastic waste generation in metric tons? And let me remind everyone that a ton is 2,000 pounds, and a pound is 454 grams. We're talking a lot, right? We're approaching 300 megatons, right, of plastic waste. That's a lot. And we're using so many different types of polymers. We're using polyolefins, polyethylene, right? Things that we use every day for containers, garbage bags, plastic bags, shopping bags, polypropylene, yogurt cups, right? Keurig K cups, polystyrene foam, PVC pipes in homes for construction, PET, recycling code number 1, right? Used in soft drink bottles, water bottles, polyurethanes. We change our mattress every 7 years in this country. There are 150 foam manufacturing companies in this country today. That polymer is not recycled, by the way. And we only have recycling codes 1 through 7, and 7 is other. Wow, that's kind of scary, right? From a molecular scientist point of view, that's really not acceptable, right? To a certain extent. Well, we have all these different polymers. We have to separate them. We have to collect them. You're going to take them out of your house and put them in the bin and take them to the road in hopes that you're doing the right thing for the environment. Every hour in the United States, we use so many PET bottles. We use 2.5 million per hour. That's per hour in the United States. That's a lot. 8 million metric tons of plastic enter our ocean every year. That's not acceptable. 9% is the recycling rate in the United States. In the world, we manufacture 660 billion pounds of plastic every year. We recycle 60 billion. We throw out, or municipal landfill, 600 billion pounds every year. There is more plastic waste on this earth than there is the weight of the total human beings. Pretty scary. But this business is huge. We employ people, we manufacture things, we make the world better. We live longer, we live higher quality lives because of plastics. I am a macromolecular scientist. I love plastics, right? That's what I do. That's what I teach. That's what I research. That's what I write proposals for. That's what I talk about at my dinner table with my poor 3 kids who have to listen to this, right? It's important, but they are here, and the legacy of any scientist is not this one, right? We don't want to leave this legacy. There's no doubt about it. Even in the last year, as we have suffered through this pandemic, and boy, have we suffered, maybe some people have suffered more than us. But the other thing that's suffering is this earth. And if we look at the amount of plastic being generated during the pandemic, it has increased incredibly high, very high increasing rates. We're going from almost a 6% growth rate in a single year for the amount of plastic being manufactured. Why is that? Well, we're trying to save lives. We're not so worried about sustainability. We're not so worried about the environment at this moment. I'm worried about my next door neighbor. I'm worried about my 88-year-old mother in Florida. We're all worried about that. But at the end of the day, we have to worry about 1.6 million plastic protective goggles, 76 million examination masks, 89 million medical masks. That's not sustainable. At the end of the day, we will face this issue. 1% of the face masks, if we don't dispose of them properly, and we've all seen them on the side of the road, leads to 10 million items on the roads. That's a lot. The demand for recycled materials has gone down, right? It's dropped. Profit margins of recycling have decreased. People are disposing of these goods illegally, right? Because we don't know what to do with them, nor do we want to pay for that disposal process. The environmental footprint of the plastics has increased significantly in the last year. At the same time, I'm talking to you as a molecular scientist. I love macromolecules. The longer the better, the more repeating units, yes, right? Those are the things I do, right, as a scientist. And we know these are important. If you've had anyone who's had a cardiovascular disease, we know the importance of an angioplasty balloon or the delivery of a stent using a polyurethane. If you've ever had a family member who has had a prosthetic device, we know that living with that is exceptionally challenging, right? And living a real fruitful life without that constantly on your mind, hey, that's made easier with the right prosthetic device, the right plastic material. And then even most recently, surgeons are practicing on 3D printed hearts so that then they enter that surgical arena, the outcomes are better. And that's the case. So there's a lot happening. There's a lot of reasons why we want plastics. We want polymers, but do we need 660 billion pounds per year of them? That's the challenge. And we need to rethink exactly what we're doing in order to make a difference. So we've all heard reduce, recycle, reuse, right? But there's a lot of RE words, right, that are floating around, like revise or re-examine or reinvent. Maybe we should repeat that, or we should reanalyze that, or rethink that, or redefine it. Maybe we should reconsider plastics altogether. Maybe we need to restore our community, or restore our field, restore our communities. Maybe we need to redesign polymers from the ground up. We need to rethink a new circular plastic economy. And I think that's the challenge. That's what we're trying to do at the Biodesign Institute. That's why this center has formed. And the way for us to tackle that is very interdisciplinarily. So the question always becomes, is it time to rethink petroleum-based polymers? Should we get rid of them? Now, I don't think the answer to that is yes, right? All those things I just mentioned to you would go away. But back many decades ago, Henry Ford hacked away at a car to demonstrate the toughness of a soybean oil-based bumper, right? It is possible to make materials from nature's feedstocks, renewable resources, and they can compete with the rational design, the synthetic chemistry of petroleum-based compounds. Now I look at this car, I think, wow, that was pretty tremendous back then, but let's look at the car of today. The car of today has over 40 different polymers, plastics in its space. 40 different ones. How do we recycle a car? I want to drive the car into a recycling center. I want to have it dismantled in front of my eyes, and I want to see those materials returned back to a new car. That's a circular economy. That's a circularity, a sustainability, right, that we hope to achieve. So before I show you a couple of research things and then I'll finish up and open it up for a conversation, I want to pose a question to you. And that question is, when you go into the grocery store, no matter what store you go to, they're going to ask you, sir or ma'am, welcome to our grocery store. Do you want paper or plastic? Now, I know everybody here tonight has heard that question. And the next time you get that question, I want you to stop and pause and think about the answer to that, because it's an important one. And as you can imagine, right, I'm a big advocate for plastic and all the chemistry and rationality and atom efficiency and all the green chemistry principles that we have emerged over the decades, right, that we have brought forth, right, really makes the plastic solution better, as we'll talk about. But what's the problem? The problem is recycling rates of 9%. That plastic is viewed as garbage. We've always heard the term one person's garbage is another person's gold. That is indeed the case. That is where we are going. Plastic is another form of petroleum. That resource can be reused and recaptured, not buried, not thrown away. That is a molecular economy, right, ready to rear its head. So that's what I want to kind of show you a little bit of a taste of some of the things that we're doing at the Biodesign Institute today. So you can imagine that we're very interested in renewable monomers. What's the word renewable mean? Well, hey, we can renew it. It's one of the RE words, right? We have a feedstock that is replenished. It's not a depleting feedstock. It's a renewable one. Those could be fatty acids. They could be unsaturated fatty acids that are screaming for organic chemistry. Let's do a reaction on them and let's make a polyurethane foam based out of a fatty acid or a lipid. What about carbohydrates, cellulosic? Cellulose is the nature's largest polymer. Let's use it. What about a biofiber? What about a composite based out of nature's fibers rather than carbon fibers, aramid fibers, other types of fibers? Most recently, I just got a research award, actually in the last month, the center has, devoted towards the 3D printing of natural rubber latex. Let's take a molecule from a tree and let's 3D print tires. And you might say to yourself, why would you want to do that? And I probably would answer, I don't know, right? But I know it's really cool. I know it's an opportunity to make the whole tire industry more sustainable. They're using chemistry they've used for decades. Time for a change. Time for infusing new molecular structure, right, into the polymers of today. Sugar-derived monomers, sugars, obviously plenty of hydroxyl groups. And what about metabolites? One of my favorite projects right now in my research group, I know I have a few students present, so all your projects are my favorite. However, one of my favorites is using a metabolite from our human body. We all produce urea, right? And there are urease enzymes. What if we could take urea or metabolites and construct polymers from them? We know they're safe for the human body. They should be safe for the environment. So lots of opportunities in the area of nature's feedstocks, which we're pursuing. Let's come back to green chemistry. And lots of times when you hear the word green, it immediately goes to a political discussion. And that is not the case for scientists and engineers. When I hear the word green, I'm thinking, don't use nasty things and don't produce nasty products. And I always come back to the 80s. If you're old enough to remember this particular cover of Time magazine, we all know the disaster in Bhopal, India, right? That disaster led to the release of an isocyanate and the death and the disease of many people in that community. That's the kind of thing we have to get away from, right? We can't use that. Can we possibly make polyurethanes without isocyanates? Absolutely. Right, give me a beaker, give me a flask, give me a stir bar, give me some chemical, I'm going to do it. Right, that is the idea. So coming up with click reactions, as the name implies, these reactions click, like the click of a finger with no byproduct, room temperature, regioselectivity, stereoselectivity, all the things that we as chemists want in designing. How about making adhesives reversible? We stick things together. Boy, that doesn't sound like a sustainability solution. How do we unstick them? What if I made them reversible? What if I made them more sustainable, right? New polymerization mechanisms, metathesis, radicals, and non-isocyanate polyurethanes. Again, let's not forget disasters like Bhopal, India, that we certainly don't want to repeat. Being in the Biodesign Institute gives me the inspiration from biology. The health of the human body parallels the health of our planet. So that's important for us. That's what motivates us. We're also working on lightweight foams. If I can replace 660 billion pounds, half of that with air, I now have a material that uses less feedstocks, less petroleum, less waste, but maybe it gives me even better the performance. I'm going to move from, for example, this kind of stochastic or random looking foam on top to something on the bottom that looks almost printed, which it is. It is 3D printed. How do we use advanced manufacturing ideas, concepts to revolutionize the types of materials we use today? For example, right now we're looking at a lot of fire suppression foams. The foam is a very big buzzword in my research group right now for many reasons, but many of those foams based on perfluorooctyl sulfonic acids, right, is PFOS, is very detrimental to the environment. It's persistent. It's found in human beings, right? Not necessarily good. What if we could 3D print that lattice? What if I could use machine learning, artificial intelligence, computational studies, and actually predict the structure of a microporous material that now uses less, maybe it's even encoded to depolymerize and give me even better physical properties than I've seen before. And finally, how can I not be in the Biodesign Institute and be thinking about materials for medicine? And it's certainly one of the pillars in this center, right? How do I address the waste issues of US hospitals? And US hospitals, as you can imagine, produce a lot of waste, 5 million tons of waste per year, 25% of which is plastic. So we're working now together with the Mayo Clinic, Charlie Rowski and my group, right? Looking at taking medical waste, refabricating it and redesigning it into high performance upcycled materials. How do we change that industry? How do we get involved? How do we partner with them? That's what the center's all about. And the center really brings together every nook and cranny on the campus. Every nook and cranny, from architecture to food science and technology to the Polytechnic campus, right? All of these corners of the campus are now looking, right, for these kind of solutions. So for example, in the last one I'll show you, these are some 3D printed tablets looking at precision medicine. How do we personalize medicine and manufacture tablets in smarter and better ways? So with that, I'm going to finish and we're going to open it up, Carrie, to a lot of discussion. I hope I got you thinking. I hope I got you rethinking, reimagining, redesigning, maybe striving for resiliency. And I'll just give a quick shout out to Earth Day, which is coming up later this month. And the title is one of the R words, right? Restore. And it's Restore Our Earth. So I would encourage you to engage in conversation, join me, come visit, meet my students, come to campus, let us show you what we're doing. And I'm always available by email and communication. So with that, I'm going to go ahead and turn it over to Carrie, and thank you so much for listening.
Great. Tim, we'll let you stop sharing your screen because such an incredible discussion. Wow. Wow. I think, yeah, Q&A. Looks like Tia might have some questions and Steve's going to help us kind of.
Okay, yes.
Excited.
All right, well, Tim, let's start with one. What about the prospects to manage all of the high density polyethylene that we already have? I mean, those are very stable carbon-carbon bonds. I mean, that's a big problem to deal with. How will we manage that going forward?
Well, you know, when I get that question, I immediately think of, you know, the leading petroleum manufacturers in the world are asking that very same question. If I visit ExxonMobil, they have now entire divisions devoted to that question, right? So it is a really super important one. And you're absolutely right. The carbon-carbon backbone is not designed to break, not unless we heat it. Every carbon-carbon bond requires 90 kilocalories per mole, right, to break that carbon-carbon bond. That's energy intensive. So could we imagine polyolefins as fuels? Could we imagine gasification or pyrolysis of polyolefins? But maybe better yet, could we just think about recycling them, right, bringing them back? Another strategy too that, you know, a lot of people are working on, and so is our research in the center, is looking at new ways to activate those bonds. So for example, the field of CH activation, right? I know there's some faculty in the room, right, thinking about that. So there's chemical ways still. We're also inserting molecular kind of scissors periodic sequences along that carbon-carbon bond, the carbon-carbon backbone. How do we make the molecules reversible and depolymerize? There's a lot of research happening, but you're right, that's a big challenge for sure.
I think Tia may have a few questions, and we can also, if there are questions from our guests here, Dr. Long, you're open for that, right?
Oh,
Q&A.
yeah, absolutely.
Anything you wanted to know.
Tim, can you hear me?
Yeah, now I can hear you great.
Okay.
Yeah.
I had a couple of questions queued up to me. So one of them is asking, are any of the so-called compostable veggie bags at the grocery store really compostable? If so, how can that process be encouraged? And this is from Paige.
All right. Well, thank you, Paige. And, and compostability is something that we, as citizens of our community, are trying to do, right? I mean, the whole idea, and I think the challenge there is to design polymers that are compostable more quickly. And if you throw something plastic into your compost bin, you don't want to have to wait a year, right, to see it go away. So you kind of want that quick reward, right, as you throw something in and you feel like, hey, I did something great for the environment. That's a big challenge. From a chemistry standpoint, what is the kinetics of that reaction? From the chemistry standpoint, how do I design macromolecules that will degrade more easily, more readily, more susceptible? How do I encapsulate an enzyme in that material so that when it goes into the compost bin, it's triggered to degrade? So looking at ways to stimulate degrading, speeding that up, and then looking at chemical compositions that when they do biodegrade, they go to a bio-friendly resource, a bio-friendly molecule. One of the more common ones these days, as maybe many of you know, is a polylactic acid. And lactic acid is one of those molecules that when you work out, and maybe we're not doing it as much during COVID, but when you work out, you get that burning sensation, right? The lactic acid will build. Well, that molecule, right, can be dimerized to a lactide, and that lactide can be polymerized to a material that is biodegradable, right? That is hydrolyzable. So the answer to that question, there's chemistry, there is getting people to do it and to feel rewarded for doing it in a timely way. I think those are some of the points I hope I addressed.
Thank you. Oh, go ahead.
So Tim, I'm thinking about two different centers in our institute. So you guys are obviously thinking about polymers, and Bruce Rittman is always looking at ways for bacteria to help solve problems. And I'm wondering if there's a way to combine the two. Could one imagine developing bacteria that are specialized at breaking down certain polymers and use them as a way of kind of recycling the material?
Yeah, Josh, for sure. I mean, the potential synergies, combining those two centers, and I've already had some discussions on that actually, and there's a lot of things happening around the Institute where we can borrow some of the discoveries from other centers and kind of infuse them into this one. But you're right, things like bacteria, things like many enzymes, even the whole biome, microbiome type of research is leading to candidates, promiscuous enzymes, molecules that will help degrade these petroleum-based polymers. So yeah, for sure, it's possible.
You certainly have that with the natural products, carbohydrates, polypeptides. Could you make a nylon carpet, not with nylon 6,6, but some kind of an amino acid polymer that becomes very biodegradable?
Yeah, no, Steve, right on track. I mean, the other thing too about carpeting, and that's one of my favorite examples because how many of us recycle carpeting? Not too much, right? And part of the reason for that too is that the carpeting involves so many different types of polymers. So one thing I've been thinking about recently is what if we could get to a place where one polymer did it all, right? Some smart polymer, right? I think one challenge is, in kind of getting at this kind of biodegradation is to get to a world of plastic that's not so dispersed, so vast, right? Something a little bit more focused. So, no, I think you're absolutely right. I mean, degrading polyamides enzymatically, hydrolytically, there's so many different ways to go after those types of materials.
We also have carbohydrates, of course, with, the starches and things of that sort.
Yeah, absolutely. And, there's even, I was just reading today about something called biochar, like taking bio-based materials like cellulosics, pyrolyze them and forming, kind of high performance fillers. So a lot of things happening in that space. I think we have to open the toolbox. We gotta, I think maybe as Josh mentioned, and you're alluding to Steve, how do we get the different centers, which may on the surface seem so different, but in reality, they're absolutely integrated. They're not standing alone whatsoever.
Perfect. So we have lots of questions. Another one is, does removing plastic refuse from the ocean really help?
Really help? I think yes. And the reason I say that is sustainability, in my opinion, is a collection of small steps. But when you have a lot of small steps together, that equals a big leap. Right. So I really believe that every little thing helps, every little thing we can do. So when we remove the plastic from the ocean, what are we doing? Well, we're preventing the ocean with all its mechanical forces and sunlight and salt from working on that plastic and generating microplastics that fish will consume. Right. So we certainly do not want that scenario. What if we developed plastics that when they saw the ocean, they degraded to a completely environmentally friendly structure? Right, maybe a fish oil. So, but back to the question, for sure, every little bit helps. Pulling it out of the ocean is big. We've all heard of these plastic islands, right, that are sitting outside somewhere in the Pacific Ocean. I don't know, is it a cruise ship that's gone by and thrown everything out? I don't know, right? But it's out there. And what do we do? And there's a lot of people working on that, trying to remove that. And it's a problem. I mean, the other thing I always think of too is just driving your car down maybe a beautiful highway along the ocean. And we know that tires will degrade, right? We buy new tires all the time for our cars. Those rubber particles are going somewhere. Where are they going? If you're driving next to the ocean or next to a beautiful lake or a pond or a bay, they could very well end up there. So I think anything that we can think about from a chemistry, science, and engineering standpoint is worth the effort, for sure.
Will your 3D printed tires be biodegradable?
Steve, I guess my answer to that right now is I hope. The thing about working on tires, and I'm just learning this because we just got this big DOE grant, is that people don't want to fool with tires, right? Because people's lives depend on those tires. So that industry is very, very cautious about anything new, right? But then in the last year, we published a paper on 3D printing natural rubber, right? This, for tires. And I can't tell you how many calls I received, right? Because that industry is clamoring for something new. So I don't know if they're going to be biodegradable because we want 100,000 miles out of them. They have to skid and not skid, and they have to have traction. But what we're doing is we're actually changing the way that chemistry is used to manufacture it. And we're eliminating waste and buffing of old tires. When I look at a tire dump, I think to myself, that is a petroleum feedstock. Yeah, those tires are thrown out because maybe part of it was bald on one side, but 80% of that tire, absolutely good. What if I could almost surgically go in and reconstruct that tire, leaving the 80% and only worrying about the 20%? I think that's possible. I think that's possible. And we're going to have to use, however, the chemistry that industry likes, unfortunately, for now. But I'm hoping, right?
Tim, I think in Arizona, they grind up those tires and mix them into the asphalt.
Yeah, that is true. That is a repurposing that people do. In fact, I think my kids have played on, those kind of playgrounds and things, where they grind up the rubber particles and put them in the play area, right? Yeah, they're repurposing them. And that's also another reword. I think, yeah, that is a viable way. I'm trying to think about how to bring everything back to the beginning, right? Into more of a circularity. Sometimes when I repurpose things, In my mind, what I'm thinking is delaying the problem. I'm delaying it. Okay, yeah, I've upcycled it. I put it in a playground. But wait a minute, what about 50 years from now? What are they going to do at the playground? Right. So my vision is really kind of long range, right, when it comes to that. But again, I'll always say every little step helps. Putting it in asphalt, putting it in the playground. Yes. Right. I think those are good steps. Right.
Perfect. So this question is from Anna Avila. What are some eco products that you approve or like?
Eco products I approve or like. Oh my goodness. There's a lot. I mean, I'm a big Starbucks fan. So I have my Starbucks app. I go to Starbucks regularly. What have they done? Well, they've done away with straws. I think that is a very visible, maybe not the biggest volume, but it's an impactful statement, right? It reminds even us Starbucks lovers that we don't need a straw, right? I can design the cup such that you don't need it. That is a product that I've seen and really, really enjoyed. I think it's a really good demonstration. What other things? I think anything we can reuse, whether it's a pouch, whether it's a container that's been crafted to be scratch resistant and retain kind of its luster. I also like the most recent BPA-free bottles. I think that's a really good example of some green chemistry, removing bisphenol A, an estrogen diol mimic, an endocrine mimic, right? How do I get rid of that? That really took a lot of new chemistry to get rid of bisphenol A. Major problem. In the last 10 years, that has been one of the shining examples in my mind of chemistry taking charge of this problem and making a difference. I think BPA-free bottles, good move, right? A lot of sophisticated chemistry in that.
Perfect. A lot of similar questions regarding what we can choose to do, which is nice. But overwhelmingly, there's a lot around our homes. What can we specifically do, and what choices that we can make regarding plastic when we have so many things to consume, use, have choices when they're made of plastic?
Yeah, it's a good question. I'm teaching a class right now on sustainable macromolecular synthesis. And I'm constantly asking the students, what are we using all the time and we don't really worry about? We throw them out. I mean, my students are thinking about appliances, right? Things that are cheaper to buy new than they are to get fixed, right? So there's a lot of sustainability in the question of things around our home. When I think of that question, I always think of consume less. Consume less. Refill the plastic bottle, the PET bottle. Don't buy more. Refill them, right? So I think there's little things like that we can do. Actually, I'm on the latest thing I'm on right now is I use less soap. I really need that much soap to wash that single glass in my kitchen sink. No, probably not, right? So I'm really looking at ways in how I live my life and how to consume less, right? And that, I think, around our house, there's so many different things, right, that we can think about.
Okay, perfect. I have another question from Kyle. He would like to know your thoughts on how far we are as an academic community from bringing truly disruptive technology we developed to such a large industry.
Truly destructive?
Disruptive.
Oh, okay, disruptive. Sorry, I was getting ready to say, I'm not sure I'm gonna do that. Yeah, you know what's funny? When I think about the whole area of sustainability, I think, oh my gosh, if we consume less, that means that plants are going to sit idle. People are not going to work as much, right? There's going to be less jobs. In reality, I think this disruption, this realization that we need to be more sustainable will create jobs. It's going to redefine the workforce. And many of the people here tonight, I'm hoping you can help me do that. Like, how do we redefine the workforce? How do we educate students, right, to be the next thought leaders in sustainability? Right, those things are happening. So back to the question about disruption, I actually think the sustainability will disrupt the chemical industry. I think it's going to force the chemical industry to redefine itself. So could we imagine maybe we no longer buy a plastic, we lease it, we borrow it. The chemical industry, the producers are actually saying, look, I'll let you use my plastic, but I need it back. right? And this is how much time you have with it. So I think it's going to redefine the chemical industry of the future. It's going to create new jobs, new directions, and new ways of doing business. I'm seeing this already in many companies, even petroleum-based companies. And many of us may immediately think, oh my gosh, you know, they're not sustainable whatsoever. That is false, right? They absolutely are, right? They absolutely are. So I think it's happening now, Kyle. I really do. And I honestly believe it's going to change the chemical industry. Their products will become their resources. I think that's the idea.
Let's go ahead now and just, if people would like to unmute and ask a question directly for Tim, I think that would be great. We're seeing a lot of kind of similar questions, but if there's one that hasn't been answered yet, and if you'd like to ask that out loud, we'd love that.
So I have,
Sorry, go ahead.
in my area, you're not allowed to recycle glass. Is it better to have a container of plastic that can be compressed versus glass, which cannot?
Well, I mean, you're getting at a couple of different things. You know, glass, it's going to require a high temperature process to refabricate, much higher than a plastic material. And you're right, you can't change the volume without smashing the glass, which wouldn't be safe for any waste management company. So there's probably a lot of challenges in terms of handling it, and then actually the cost of converting it back, right, to something. You might say, well, can't you just wash it out and use it? That's a tricky question because, you know, many of those things, people may have poured gasoline from their lawnmower, right, into that jar. You don't know, right? So there's a lot of challenges with plastic materials. They are susceptible to relatively low temperature organic reactions, right? So I can hydrolyze a polyester at, you know, 200 degrees C, right, for example, or I can depolymerize a polyurethane mattress at temperatures as low as 65 degrees C. So I think there's this whole discussion of energy, cost, you know, infrastructure. I mean, I think all of that kind of factors into that question. It's the term we like to use is called life cycle analysis. How do we factor in all the elements of that material and see if it economically makes sense? I think that's a strategy. That's probably what's happening in your neighborhood, I think, perhaps.
I have a question, if you can hear me. Am I on?
Yes, you're on, Chris. Go ahead.
We think in terms of biodegradability so much with plastics, but what are the options? Well, how many sort of pathways are there to degrade plastic? Do we need to be thinking only in terms of biodegradability, that is subject to maybe digestion by microbes, or are there other degradable processes, pathways that we can target to develop technologies for?
Yeah, Chris, I mean, you're really pointing to a cutting edge theme right now. So I can tell you every day I'm getting a new request for proposals on what's called depolymerization. You know, how do we take molecules apart? I mean, I think recycling is wonderful and we all should be doing it, but we're still sitting at 9% recycling rates after decades of trying to do this, right? So what does that mean? So I think you're right. I mean, one of the big pushes right now is to expand kind of our toolbox of unzipping it.
Yeah.
You know, taking it back. Like, it's almost like in my mind, if we can get oil out of the ground and refine it, why can't we take plastic material and refine that? It's just that we put the carbons and hydrogens and oxygens together differently, but still, you know, pyrolysis, gasification, hydrolysis, aminolysis, there's organic reactions galore, right, that can be used to reverse these. You know, the other startling thing too, Chris, I think about is like polyethylene terephthalate, recycling code number 1. In the United States, we recycle that 25% of the time, 25% of the volume. If I was to visit Japan or Sweden or Germany, recycling rates are 80 or 90%. So what are we doing as Americans? Sometimes I wonder about that, but the point of me to say that is that polymer can be quantitatively pushed back right to its petroleum feedstocks. It's completely circular. So, you know, what you're getting at is, yeah, you know, that needs to be a pillar of our research center, and it is. So spot on. I'll ask you to contribute to my next proposal if you don't mind. How about that?
By all means. And may I ask a second question? It's quite different. I've written it before. I often wonder this, and I think a lot of people probably think about it. We draw oil out of the ground and we think of it in terms of fueling our transportation systems, but it's also feeding the plastics industry. And so I'm wondering, even if we could electrify or make our transportation system entirely independent of fossil fuels, we still would require fossil fuels to build plastics. Roughly, do you have a sense of whether it's 5%, 1%, 50% of the oils that we draw to the ground are going into the plastics industry versus the fuel?
Yeah, I mean, great question. The lion's share goes into fueling our cars and cooling and heating our homes, right? So a lot of it happens there, but you're right. I mean, the answer is not to say no more petroleum. I mean, I think that would be just a huge mistake. I think the answer is to use petroleum in a circular way, right? To use it and return it, right? In some circular way. So even though the plastic may be 10% of the total use of the petroleum feedstocks, right? Because we're using driving and heating our homes and things like that, and running chemical plants and other things like that, we got to have petroleum. Right? I don't think in our lifetime for sure, and for lifetimes to come, I really don't believe that's going to go away. I mean, I think we're going to, electric vehicles, yes, we still need light materials to let that electric vehicle go. We still need batteries, right, made out of petroleum-based products, right? So yeah, the answer is definitely not, no more petroleum or something. The answer is to use it more smartly and more circularly. I think that's the key.
Thank
I
you.
think we have time for maybe one or two more questions from perhaps something that hasn't been spoken of yet. Is there a question out there that's burning to be asked?
I have a question. Sorry.
Great.
Dr. Lang, I am a K-12 educator. I teach at high school. So I see that through my science projects, a lot of students are very interested in bioplastics. So what do you think is the future of bioplastics in our industry? And how do I motivate my students to do more research on these kind of things that you're working on, macromolecules? I mean, being a 9th grade teacher, and honest, I teach macromolecules all the time. So how do I incorporate your research in my studies so that the students get motivated to do research more? And thank you.
Well, you got to come over and talk with me for a few hours. I think that's, I would love to have that conversation with you.
Absolutely.
The first thing I do, I mean, some of our most, eco-conscientious people are people who are young, right? They see the earth and they see years ahead of them and they want it to be the same. One example I always bring out with younger students is the idea of sutures, bioabsorbable sutures, and kids can really relate to that, right? They're saving lives. It's a plastic, but it's being used to kind of suture and stitch inside the human body, and I think that kind of captures their attention to a great extent. I also think architecture and art is another interesting avenue. Like, so for example, there's many examples online, and that where people have used plastic to create artwork. I have this vision of using plastic to create a house. I want the entire house built out of recycled goods, right? So I think when it comes to kids, I think they want to see, kind of a quick, kind of appreciation for. I think the healthcare industry is quite big for them, even though they're young, they know the importance of it. But I also think things like art and architecture and construction, and I think those kind of really visible things, right? Maybe some different things might attract them.
Interestingly, you talk about bioabsorbable sutures. This was one of the projects that actually went to Regeneron Talent Search, and this was not just a biodegradable, bioabsorbable, but also color-changing sutures that would indicate infection. So very interesting things coming out of high school. So I'll definitely talk to you soon.
No, I mean, I think you're totally right. Like, stimuli responsive, or if I stretch something, it turns color. So that means like after it's worn out, it's slowly turning black or blue or something like that. That's a whole interesting field of kind of self-healing. Like when I think about the human body, if I break something, but then I set it aside, will it quickly reshape and reconnect itself? Right, so maybe that idea of how does the human body ensure sustainability? What are its principles? And how can we take that into things that we use every day? I mean, maybe some thinking like that might help. And thank you for surviving during this time of teaching. Big shout out to your teacher.
I actually do enjoy it, and I'll talk to you for sure.
Okay.
Great, great. We have just one last, so many questions have flowed in. I just want to let folks know that questions, if they haven't been answered tonight, we can work to see about some of those questions. You can also visit the Biodesign website and actually go to Dr. Tim Long's site and to learn more and to connect there. But just one last thing to go on, and then we can kind of round out the program tonight, and I'll turn things back over to Steve Monk. But this question from Sandy, does the circularity still add to greenhouse gases? There's been a lot about greenhouse kinds of things, and that's one topic that perhaps if you could briefly comment on that as we round out a Q&A tonight.
Yeah, I mean, really, it's a great question. You know, you're thinking about carbon footprint. You know, how much CO2 is produced, right, for a certain process. And what you're getting at is, you know, kind of life cycle analysis. And if we, in fact, you know, have this circular economy, yes, there are people at ASU who have devoted their careers to understanding that techno-economic analysis or life cycle analysis. So you're absolutely right. As we heat something up and we need energy to do it, we are producing CO2. So that is a concern. I mean, so it factors into the whole sustainability equation. You know, is what I'm making truly sustainable? It's the paper versus plastic kind of conversation. So you're right. There's a lot of, you know, kind of entanglement between, you know, CO2 release, you know, climate change and sustainability. But I think for sure, sustainability is something we all agree on, is that, you know, that's something we need to do. It's one of the greatest challenges to the environment of our time today. So let's get after it. Let's do it.
Thank you very much, Tim, for a really exciting and interesting talk on a very important subject. I'd now like to take a moment to introduce my colleague, Elizabeth Munkle from the Foundation, who will give us a little bit of an intro there.
Thank you, Steve. As Steve mentioned, my name is Elizabeth Munkle, and I have the great pleasure of working with the Biodesign Institute on behalf of the ASU Foundation. Tonight, you got a glimpse of some of the amazing work taking place every day at Biodesign, and we would love for you to join us in making this work possible. One way to accomplish this is to join our Pioneers Circle. The Pioneers Circle is comprised of scientific enthusiasts, curious knowledge seekers, and committed philanthropic supporters who invest in Biodesign's groundbreaking research. Your gift of $1,000 or more annually empowers our teams to take on the most pressing challenges to our health and environment. Philanthropy plays a unique and vital role in our work by allowing our researchers to explore new and untested frontiers of disease detection, drug therapy, and sustainable materials like you heard about tonight. To learn more or to join, please contact me or visit the website just added in the chat box. Thank you.
Thank you very much, Elizabeth, and thank you, Tim, for a really wonderful talk. I'd like to thank the events staff for putting on a really wonderful evening tonight. And if you enjoyed this, we have a lot more for you next year. So we have an exciting lineup coming up in the fall. Please save the dates. I'd also like to encourage you to take our survey, which you will receive via email. We'd really like to hear your comments. I'd like to thank everybody for attending tonight. It was really a very interesting and informative evening, and I wish you a good night.
Thanks all for joining us.
Thanks, everyone.
Thanks, Tim. Thanks, everyone.
Good night, everybody.
Good night.
Good night.